So we're going to talk about mathematical models of networks. And what we're going to do today is we're going to talk about models. Before we jump there, let's discuss networks, right? The main properties, the main features. So there were like several main features, and we talked about it last time. We talked about power law degree distribution. Remember that? Okay. Then there was a small average distance or graph diameter. Then there was clustering coefficient and gigantic connected component. Let's quickly go over this. Power law, what is that about? Oh, come on. Some of you were last time in the lecture. So what's power law? So the degrees of the nodes are distributed according to the power law, but in plain English, what does it mean that they distributed by power law? What's the main sort of property we expect from that?
The degree decreases, so the number of such degrees decreases with size.
So yeah, so in other words, what you would expect from this type of graph is that you have a lot of nodes with a low degree, and you will have a few nodes with a very large degree, but like really, really large degree. And again, you should think about social network and let's say celebrities that have a lot of connections, a lot of friends, a lot of people following them, and then just sort of, regular Joe, all right? Okay, now, small average distance or graph diameter, what's that about? Oh, come on, happy crowd. So what's small average distance in the graph? What's that property? In plain English, we also talked about it. Who was actually in the lecture last time? Come on. Oh, did we completely change the audience? So this is a social network analysis. Are you guys here for the social network analysis? Yeah, I know you were last time. So do you remember what small average distance is? What that about? No, okay. One more time, 6 degrees of separation, right? 6 handshakes that separate the world. It is the fact that in those type of networks, there is usually very, very small diameter, so it takes only a few steps to reach from one node to any other node, right? And we actually calculated even last time that takes only 6 handshakes, and you can connect 7 billion people, right? And there was this story about large clustering coefficient, and there is this word transitivity. That's additional bonus question. So do you remember what that is? Triangles? Anything? All right, so that's the main idea there is that if you have 2 friends, right, there is a very good chance. So if you have 2 friends, there is a good chance that they know each other, right? So the fact that there's a lot of triangles, that means if you know one person and you know another person, there is a very high degree probability that they know each other. And so if we're talking about social network, there is a connection between you and this person, you and that person, and they most likely will be connected too, all right? So the fact that there are a lot of triangles. And gigantic or giant connected component, that means when you look at the graph, most of the nodes will be connected. You'll be able to get from one node to another. That will be like the biggest part of the graph. Now, guys, I'm going to be repeating those properties. I'll probably start every lecture with them until you actually memorize this, okay? So I strongly suggest you to start doing it now so you not get bored, because if you hear this, on the 10 lectures in a row, that probably will get pretty annoying. Okay, so we're going to talk about models today. And in fact, we're going to talk about what's called generative models. But before we go into that topic, just a question for you. Why do people make mathematical models? Why do they do modeling? What's the point?
Well, for example, to justify their theoretical view, to get them to that way so they can justify the theory they constructed.
Okay, so for example, to justify the theory, right? The theory they came up with, it's because they believe the world is built in a certain way. They create a theory and then they want to verify this theory. Yeah. Anything else? Predict something. Get a simplified picture, right. So what's actually a model? You know, model is a simplified picture of a reality, right? You don't want to make your model as complex as reality because, well, you do have a reality, right, in many cases. And so it's much easier to make experiments with reality than try to actually completely reproduce it within your model. So there is a certain extent of granularity. There is a certain extent to which we go to actually make model exactly reproduce real world. In fact, very often we want to make model quite much simpler than the real world so that we have certain parameters we can tune, right, and see how it affects everything. Because if you have a very complex model, you have lots of parameters, right? And then it's going to be very, very hard to make any experiments and to verify any theories. But if you believe that there are certain things that are very important, right, and the rest is less important, you actually introduce those as a parameters to the models, and then you can control them and see how those parameters affect the result. But in order for that to work, the model has to be simple, relatively simple. So what we want from model is that it does reproduce the reality, but we don't really want it to be like, very, very completely comprehensive, right? And we don't want it to reproduce reality precisely. And so we can actually build different models that reproduce reality better. Some properties, they reproduce it better, right, for the reality. We don't need to have a model that reproduces everything perfectly. And so the other thing is, with models, you can actually start with a simple model and then build on top of it, right? You can take several models, you can merge them, you can take a very simple model, then expand it, etc., etc., etc. So what we're going to talk about today are actually three basic, simplest models. So they're not complicated, and they do not reproduce reality perfectly, but they give you good intuition about the networks, right? In fact, those models been created in very, very different times. So the first one we're going to talk about is the random graph model. It's been created by famous Hungarian mathematician Paul Erdős and Alfred Rényi in 1959. And they actually, pretty much two of those guys created the whole theory of random graphs and random networks. We're then going to talk about two more models. The model, small world model, created by Duncan Watts and, and Strogatz. There's two American scientists, 1998. And then we're going to talk about preferential attachment model by Barabashi, Laszlo Barabashi and Reka Albert. He's actually also Hungarian, but they're right now in US, 1999. So they're all very simple models. And they've been designed to try to actually, like what you said, to see if we understand the networks. So there is some theory, some hypothesis about the network, and we're going to follow this hypothesis. We're going to build the model, and then see if this model describes the network. Now, there is this word which is called generative. What does it mean? So the meaning here is actually going to generate things, right? So all these models, they actually generate graphs. They're generators, right? This is a model. Based on this model, we'll be able to create graphs. Okay? All right. So let's start with this random graph model, probably one of the most famous models. And the idea is the following. Imagine that you come to the party, right? And it's a big party, and you don't know people. You don't know anybody, right? So you don't want to hang out alone, so you start sort of making contacts, right? So, you pick up. Look around, pick up somebody's, glance on somebody, you start talking, right? You might glance on some other person, he will ignore you. But with somebody, you got the eye contact, you start talking, all right? Then there's somebody else comes in, they start talking to other person, somebody else to another person, et cetera, et cetera. So you got the sort of pairwise connections, right? After a while, you might stop talking to this guy and, for example, form a connection with another person, and et cetera, et cetera. And by the end of the party, you will actually know a lot of people. So that's sort of the live situation. Now, the idea here is in this very, very simple experiment that you're making your connections quite randomly, right? You just sort of look around, oh yeah, let's talk, right? Mathematically, how can we represent this? Let's say you have a bunch of nodes, and here I think there is like, what, 12 nodes. And here is a process that we're going to follow. We'll go through all the possible pairs of nodes, And by the way, if there are 12 nodes, how many pairs of nodes can we form here? Well, that's the right answer. How do you know that? Okay, well, all right, fine. You know the formula, but if we don't know the formula,
we just take one node. We see that we can connect it with possible n minus 1 nodes. Then we should multiply n by n minus 1, and then divide by 2 because of the symmetry.
That's correct. So let me repeat this, guys. And this formula we'll use it over and over again. So, let me go slowly through this, try to understand, right? So the idea is the following. I'm trying to compute how many pairs I can form here, all right? So I can take this, for example, node. I can start with this node and form a pair with this one, right? There's going to be one pair. I can take this node and form a pair with this one. That's going to be a second pair. That's going to be a third pair, fourth pair, fifth, etc., right? So how many of if I fixed this node, right? I selected this. How many pairs can I form with the rest of the circle? 11. All right. Good. Now, then I can take this guy and go through the same exercise. How many pairs can I form? 11. Right? I take this guy. How many pairs can I form? 11. I can take this guy. 11, 11, 11, 11. All right. So how many ways to pick this first person? 12. And for each first person, I can form 11 pairs. 11 times 12 is 132. All right. So it's 11 times 12. That's how many pairs you can form. But there is a catch here. What's the catch? There is a little mistake we made. We counted each pair twice because when I said pick up this guy as the first guy and go through all the pairs, let's say I counted this pair. When I said pick up this guy and go through all the pairs, one of the pairs would be the pair with this guy, right? So for each pair, I counted it twice. I double counted. So to actually have a correct number, I have to divide by 2. So overall, the number of pairs that are possible is 12 times 11 divided by 2. 12 divided by 2 is 6. 6 times 11, 66. All right? So it's actually surprising that you see, this is not many nodes here, but if you start calculating pairs, there's actually 66 pairs you can form. 66 different pairs. All right? So, for example, I don't know how many people here. 40? Yeah, sort of. So how many pairs can we form? 40 times 39 divided by 2, right? 40 by 2, 20, 20 times 39. So that's how many pairs we can form. So it grows really, really fast. So that's the total possible number of pairs. Now, when we build a random graph, what happens is the following. For each possible pair, there is a probability that it's going to be formed. All right? Let's say if the probability is 50%, the easiest way to think about it is you're flipping a coin, right? Let's say, we're going to look at this pair. We flip a coin. If it is tails, let's say, there is a pair. Boom. Now, we look at this one. We flip a coin. Yeah. No pair. We take this one. We flip a coin. It's again heads, no pair. We take this pair. It's, tails. We form a pair. And so on. Okay? So if we do that, and there are 66 possible pairs, and the probability that there will be a connection formed for every pair, how many connections do we expect to have? Speak up. 33. 33, half of them, right? Because if the probability that the pair is going to form or not is 50%, well, that means we go through all the pairs, half of the connection is going to happen. All right. Now, what we see here in this graph is there are 12 nodes. The probability that there will be a pair in between any two of the nodes is 1/6. Right? Now you know math. 12 nodes, probability 1/6. How many pairs, or in this case, edges or links, do we expect to see on this graph? Around 11, right? Now, it's expected number because it's still a probabilistic process. It's a random process, right? So, you might get 11, you might get 10, you might get 13. It's possible because it's a probability that you're computing. But, on average, it should be around 11. And that's what you see. So what you see here is we run this process, the process I have described three times. Okay? And the first time you get this graph, the second time you got this graph, the third time you got this graph. Make sense? Okay? It's like, again, you're coming to 3 different parties with the same people. You start all over again. You just introduce yourself to different people. Now, that doesn't look very interesting, right? I mean, there are most of the connections, there is a connection here. Well, okay, you might probably follow through this path, but that as far as it gets. What's interesting is when you actually look at the larger graphs, and this one is 100 nodes, and the probability here is 0.003. So that's a probability that when you pick up a pair, there's going to be a link formed between them, right? It's only 3%. And there are 100 possible nodes. So there's 100 times 99 divided by 2 pairs. And then you'll see interesting thing. You will see that the graph is actually the one you got here is connected. So you pretty much can get from any node to any other node. So in some sense, what it also means that if you're at this imaginary party, and there is a pretty high probability that you're connecting with people, and 50% is actually very high probability, then after a while, the graph will be connected, right? And what that means, for example, if you tell one person a secret, and just tell one person a secret, guess what's going to happen by the end of the party? Yeah, everybody will know it, because everybody will be connected to everybody, and then that person will tell one of his friends, and he'll tell one of his acquaintances, and the whole thing will connect it, and so your secret is gone. And that's why, by the way, that's why you don't want to gossip at the parties. It's eventually going to come back to you. So that's sort of the very simple explanation of what random graph and the random graph construction is, right? That's a random graph model. Now, why would I bother spend so much time on this? Well, because, first of all, it does have some sort of interesting properties like we just described, but it also has some very, very amazing property. And we're going to talk about it, and that's why this model caused so much attention. Before we go there, I still want to give you some formulas, all right? I know you don't like formulas, but bear with me. So graph is actually, again, is defined by nodes and edges. And this is a formula we have discussed with you on the previous slide, which is if you have n nodes, then this is the total number of pairs that you can form, n times n minus 1 divided by 2. And then P is a probability that when you form a pair, that they'll be connected by an edge or a link. Now, as we did before, we multiply this probability by the total number of pairs, and we get expected number of edges in the graph, expected number of links that are all going to be formed, right? Like we did on the previous slide, 11 nodes. What do we calculate, right? 11 times 10, multiplied by, for example, by 0.5, right? Or 0.3. So that's the average number or expected number of edges that we'll have in this graph. What's actually more interesting is that by using this very simple math, we can also estimate the average node degree in the graph. And again, node degree is how many on average connections every node will have, right? How many friends you will have. And the way we do it is just 1 over n divided by 1 divided by n and sum over all node degrees. And last time I showed you the formula. It's 2 times m divided by n. If you take this and plug it in here, n cancels, 2 cancels, and you get the average node degree is p times n minus 1. And if n is large, it's approximately equal to p times n. So what it means, if you have 100 nodes and you create this random graph by the process I have described, and the probability that there is a connection being formed is, let's say, 5%, you'll get, on average, the degrees of the nodes that you will have in the graph will be 5. Okay? Make sense? Sort of, kind of? Just stop me if you don't understand something. Now, so what's about that amazing property of the random networks? Well, it happens that when depending on this probability with which you connect every pair, your graph will have very different structural properties. If the probability is less than certain critical number, and we will learn what that critical number is, what you will have is those little small islands of connected nodes, right? So it's like I mentioned, you come to the party and you'll meet some people. There'll be some pairs formed, but overall there will be no connections to the entire party. Now, left to the right, if we increase this probability for 2 pairs to connect, then at some moment we'll start seeing a lot of connected nodes. See this animal here, right? It goes through a pretty big chunk of the graph. And then when you go and increase this probability even more, all of a sudden most of the nodes will be connected. So graph goes from the situation when it is disconnected, when you construct it, to when it is becoming almost fully connected. Now, and that happens very, very fast, very, very, very fast at some critical value of this probability. In some sense, this is very much, this is called phase transition. It is very much similar to, phase transition in physics. Can you give me an example of a phase transition that you learned in high school? Okay, let me see. Anybody else remember this? Boiling water, water to gas. But the also very good example is water freezing water, right? The temperature is decreasing, nothing happens, right? It's in the liquid state. Nothing happens, right? It's 2 degrees, okay, it's 5 degrees, it's cold, at 4 degrees it's cold, at 3 degrees it's cold, at 2 degrees it's cold, it's 1 degree it's cold, it's 0, then boom, and you got ice. So the same happens here. You kind of increase, instead of temperature, there is this parameter, the probability that people will connect, right? And it's slowly increasing, and nothing major happens. You still have a lot of separated pairs or couples of people. But when you hit the threshold, instantly you get the graph connected, right? All of a sudden, everybody will know everybody. And that's a very, very striking property. And that's what amazed back in the days scientists, and that's why they start studying this. It's actually a very cool property, and you can literally observe it. Now, the way to observe it is very easy. Within R, there is this function R-Rene, well, it's called game, whatever. It's a generator. And you can, as a parameters, you can put this, well, the number of nodes and the probability that 2 pairs are connected, right? And then you can just see, and then you can count how many, you can count the size of this largest component. Or, in other words, for example, you can take the largest component and see what the fraction of all nodes that belong to this component. And you will notice that at small values of p, they're quite disconnected. Then there is a pretty big fraction in there, and then all of a sudden, most of the nodes becomes connected. And you can actually observe it. It's sort of numerical simulation, numerical experiment. This graph, this picture is generated from that function. Does it make sense? Any questions? I don't see excitement. There's a phase transition. Come on. People, how often do you see this? It's like, I don't know, like when the economy collapses, right? Like in one day, right? That's pretty much the power of this. Okay. So, as I said, this parameter P, the probability that the connection is being formed, that's what controls the graph. When P is equal to 0, it's empty graph. There is no nodes. I mean, there's no edges at all, right? Because it just says, it doesn't matter how many people in the room, they never connect, right? The probability of connections is 0. They're still lonely. P equal to 1, within our process, it means we're going to get what kind of graph? It's a complete or full graph because it means every connection happens, so every node will be connected with every other node, right? So it's very, very dense. And then in between, we're going from this phase when everything is disconnected to where everything is connected. And there is a lot of interesting mathematical properties. When P is less than critical, the maximum size of the component will be like logarithmic of number of nodes. Then when it is next to critical, it's going to be n to 2/3. And when it is greater than critical, it is of order of n, which means all nodes will going to be there. And the theory actually gives you this critical value. And the critical value is when this number P, which is the probability of connections, times the number of nodes in the graph is equal to 1. Or in other words, because we started like a few slides back, we showed that this P times n is average node degree. It actually says when average node degree exceeds 1, you start getting this connected, very well connected graph. Now, let's think about this. Average node degree, what is this? It's on average how many friends, how many connections every person has. So what does it mean that K on average start exceeding 1? If it is less than 1, every person has, most likely one connection or no connections. If you have one connection, you're connected to one person, right? It's a pair. But if on average you have more than one connection, you can be connected to this guy and to some other guy. Well, that other person can be connected to you and to some other person. That person can be connected to his and to some other person. And so all of a sudden, the whole thing can become connected. See that? Okay. And so there is this critical value, which is average node degree is equal to average node degree is equal to 1, and that's when this phase transition happens. And here is also an example. We see on the left a graph. So what I'm showing here is the following. On the x-axis, this is average node degree in the graph, or that parameter P, right? Remember, P times n is this K. So that's what's shown here. Here it's equal to 0, 1, 2, 3, 4, 5, right? Again, it's much easier to think about this as average node degree. What I show here on the vertical axis is the ratio of the size or of the number of nodes that belong to the largest component divided by the total number of nodes. So what the fraction of the total number of nodes are connected. So what happens is when we're here, this fraction is equal to 1. Everything is connected. When we're here, they're mostly disconnected and this fraction is very close to 0. But when this parameter K, or average degree, is equal to 1, starts from 1, you all of a sudden start getting connection, and it goes very, very fast. And pretty much in a very, very small interval of K values, the fraction of the nodes that becoming connected goes from 0 to 1. If you, out of curiosity, search for like phase transitions in physics, you most likely see this type of pictures, right? There will be certain parameters that behaves the same way. And that's what actually sort of made these models very, very famous. The fact that these models, in spite of its simplicity, it actually describes very complex phenomenon like phase transition. And there are a lot of phase transitions in physics, from conductivity to superconductivity, from water to ice, from water to vapor. So there are quite a few examples. Any questions about this? Now, so for you, what you need to remember out of this whole story on random graph and random network is there is this way to build a network with randomly connecting pair of nodes. If you do this, you'll have a random network with certain properties. And if the probability of connections is small, you'll have a lot of disconnected pairs, right? And if the probability of connection is greater than critical, then the whole thing will be connected in one large graph, okay? Where every node is reachable from every other node. Make sense? Okay, good. Now, we also talked about different properties of the graphs, and we're not going to go into the details. We're not going to compute them for this graph, but I'm going to just tell you what they are. Now, of course, this is one of those random graphs, right? And you can actually calculate node degree distribution, which is how many nodes of which degree we have. How many nodes of degree 1, how many nodes of degree 2, how many nodes of degree 3, how many nodes of degree, 20 we have here. And for the power law graphs, this picture, this graph would have a lot of degrees, a lot of nodes with low degree, and a few nodes with a very high degree. A random graph doesn't have that property. Random graph has what's called Poisson distribution of the node degrees, which is there is a very explicit peak in that distribution, which is majority of the node has certain degrees, and there are some nodes with low degrees and some nodes with high degrees. So it is different from this power law. So this model does not reproduce the power law. Okay? And in real life, we do see this power law. Let me see. I don't have it, I guess, here. Okay. This model doesn't reproduce the power law. Now, in terms of the size of the small world phenomenon, right, the diameter of the graph, we did this exercise on the previous lecture. Notice that at the beginning, when we start building this network, before it gets very dense here, it looks a lot like trees. And tree means it's a graph where there's only one way from each node to every other node, right? So it's this kind of structure. So for those structures, what we can estimate easily how many steps it takes you to reach from any node to any other node. But even without sort of doing mathematical formulas, when you look at this, you might notice that, how many nodes are here? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Probably 8 here. Well, probably around 30 nodes, right? I mean, you can count if you want to. What's the diameter of this thing? Well, actually, I don't know, but 1, 2, 3, 4, well, there's like 5 or 6 steps you can get from any node to any other node, right? So it's actually pretty small in this structure. And so you can actually calculate and show that the diameter, when you have this type of tree structure, is actually going to be proportional to the logarithm of the number of nodes. And that's a small world property. So the fact that when you have a lot of nodes, but if they're connected in this type of structure, then the diameter will be small, or average path length will be small. And we talked about it on the previous lecture. We actually estimated for the real world, the situation. So the key message here, you can have a lot of nodes, but the distance between them will be small. And small means like logarithmic in terms of number of nodes. Oh, and by the way, last time I asked you to check what logarithm is in the textbook. Have you done that? Do you remember what logarithm is? Yes? No? Okay, I take it that everybody knows what logarithm is. All right. Okay, finally, this clustering coefficient. Clustering coefficient tells us how many triangles are, or it also tells us that if you have two friends and if two people have a friend in common, what's the probability that they know each other, right? So this triangle story. In this type of graph, the probability that two people know each other does not depend on if they have somebody in common. Because remember, the way we build this model, we take two nodes and just flip a coin, right, and with some probability connect them or not. So we never asked like if they have friends in common. We just connected them, right, or not connected. So the clustering coefficient here is actually equal to that parameter p, and it does not depend on anything within the model except for this parameter p. And so it can be actually quite small if this parameter p is small. So in plain English, in this type of graphs, there will be very few triangles. So in some sense, this model actually does not describe triangles the way we see it in the real social network. And the distribution of node degrees is also different from social network. But it gives us this small world phenomenon. The fact that there is only a few steps that can take you from one person to another. And that's the contribution of this model to the theory, plus of course this whole story about the phase transition, which is actually very cool. Okay, any questions about this model? We're gonna go talk about the next one. So if you have any questions, please, it's time to ask. Okay, all right. Okay, so next model. Now, I gave you a certain sort of explanation or model of a human behavior at a party, right? It's a little bit artificial in a sense that, I kind of forced you to think there's a certain number of people at the party, right? And then, you're making certain connections. So let's think what's missing or how real life is different from that model. We can think about it in terms of, party, or we can think about it in terms of, Facebook graph, friendship graph, whatever. So what's in that model, the one I described, what doesn't feel right? I mean, what doesn't feel natural? Think about how party starts, right? Or think about how friendship evolves on the network. So one thing is, I said you don't know anybody, but it might be that you know somebody. Yeah, is it possible? Yeah, you could probably start with some already connections. That's true. What else? But there's a few fundamental things. Can you speak up? I cannot hear you. That's a very good point. Notice, in our previous model, I said, hey, here's the nodes, and let's form connections, right? But if I think about party, it sounds like, okay, everybody walked in at the same time, right? Like on a big conference, everybody was waiting there and then just walked in at the same time. Well, that's not what usually happens, right? You usually get one person arriving, second person, third person, so you get dynamics, right? You get people coming. The same thing with social network. If you think about Facebook graph, it's not like it instantly got, how many? 2 billion, 3 billion, I don't even know how many users they have right now, right? Several billion users. They grew with time because people were joining, people joining daily. Okay? So that's one very important difference. We had this sort of static model. Life is dynamic. What else? Very good point, yes. So what could happen is that, at some point, party ends, right? And, you had a couple hours, you didn't use them, you don't know anybody, well, that's it, go home, right? Valid point. What else? We'll never have full graph. That's also correct. And probably, this going home thing will prevent us from happening also. Anything else? But think about your choice. When you come to a party, do you actually randomly select a person to come to and talk to? You either go to popular people, right? You see like a group of people and you join them. Maybe you come to somebody you know, but I mean, you probably go to completely random person only out of like total despair, right? You don't know anybody, you don't know what to do. Okay, fine, that's my victim, right? So, these are all valid, very valid assumptions, and you can actually build models and use all of them, all these assumptions and constraints. So Barabash and Albert used two of those, actually three of those that we described. One is they wanted to have a dynamic model, which is the model changes with time, which means nodes arrive with time. Second is when there is a connection being formed, a node, a person, selects which node to connect to. And the way it does is very simple. In this case, it's very much sort of a greedy approach in the sense that it looks around and it connects with a higher probability with a node that has higher degree. So it's still not like, okay, this is the largest group I go to, and I connect to the guy in the center of this group. But it is more like, okay, here are the several groups. There is still some randomness. I can still go and connect to any of those groups or any of those people, but I will have a tendency or higher probability connecting to the largest group. Okay? And it also starts with some initial small structure. It doesn't start empty. So these are the assumptions they put into their model. Model circa 1999. Since then, there has been tons of PhDs, diplomas defended by students adding different extra constraints to these models, right? You don't have to, you don't join, I don't know, you calculate the ratio of guys and girls in the group and, based on that ratio you join, right? You join the group where you know a few people, you join the person who knows the person. I mean, you stop joining after 2 hours. So whatever constraint you can come up with, you put it in there, you create your model, you call this model with your name, you run with it. If you can convince people that this is a great model, you can even publish it. But that's like the story of previous 10, 15 years after that model. But this model was sort of the model where that started this whole thing. Okay? So at first there was this random graph model, which was very, very simplistic in the sense of this dynamics. And then we had this preferential attachment model. And it's preferential attachment because when the new node comes in, it chooses where to be attached to, right? And it prefers nodes with a high degree. And that's where the word preferential comes from. So, dynamical growth model. At 0 time, there are some nodes, and there might be some edges. Growth, on every step, we add a node with some number of edges, and that node connects with those edges to other nodes. It's slightly different from this party situation, where in the party, you come with one edge, in the sense you connect to one group. Here, it says, well, you can come in with like 3 edges, which means you can simultaneously connect to three groups. It's just another parameter in the model. And then there is a preferential attachment, which means the probability of connecting to a particular node is proportional to that node degree. Okay? Again, it does not mean that you only connect to the node with highest degree. It just means you're more likely to connect to the node with a higher degree. So here's a picture. Let's say you start with this simple structure, this scale-free model. There's 3 nodes, and then there is a new node comes in. All the nodes here have the same node degree, so it just connects to one of those. Then there is another node comes in. It can actually connect, to any nodes, but it most likely will connect to the node with a higher node degree. And at this moment, this guy, because this one already connected to it, so the node degree became higher. So this, for example, can connect to this node. And so on and so forth. And that's how graph evolves. Yeah?
So we all of a sudden we know the same degree is equal to 2, right? On every step.
Every time, yes. So the model, what the model does is every time you get a new node, the newcomer, it always has the same number of free edges that it can use.
Step 2 we add only 1 edge.
I think there were 2 because it just overlaps. So it actually connected. See, it connected to this one, and that's why these guys, both of them, got bigger.
Just not discernible.
Yeah. Do you guys understand what the question was? What he was asking is that here, when the node came in, it always comes with 2 edges. And here you can barely see it. So there is 1 edge coming to this node and 1 edge coming to that. And that's why this and this looks bigger here, because they got connected to this guy, right? So the node degree became larger. And that's how graph evolves. Okay? Make sense? All right. Now, what's interesting and kind of sad in this picture is that, of course, you can calculate how node degree will evolve with time, right? Because within this process, there are some nodes, and the node comes in and connects and connects and connects. And we kind of talked about this from the point of view of incoming node, right? But after the guy already in, right, there are other people coming in and connects with him. So his node degree is growing with time, right? So, his number of friends, it grows with time because the new guys coming in, they're connecting to him or to her. So what happens is the following. Let's say there is this green node came in at time equal to 10. And then what you can show is that the node degree within this model will grow is the ratio of what time it is divided by what time it is when we check it, divided by the time of arrival, and there's a square root here. So it grows like this. The way to read it is if at the time the node came in, let's say at time 10, it had degree, whatever it was here, like 3, then at time 60, most likely the degree will be around 6, and at time 100, the degree will be 8. And then there is another guy arrived at time 20. Well, at time 40, the degree will be 4. At time 60, the degree will be 6, etc. Right? And then there was somebody else arrived later. So these are the degrees at different moment of time, nodes that arrived at different moment of times. This is the earliest arrival. This is next one. Okay? Again, think about it as people who are, you arrived at the party, you made your connections, right? You made your first, whatever, let's say 3 connections, and then you're just waiting because other people coming and they're connecting with you. Now, why do I say that this is a sad picture? I know I should have drawn a smiley there or something, but let's see how far you can interpret this.
Because degrees are always increasing, there will be no power law.
Well, degrees are always increasing. Why is that sad? I mean, this is fantastic, right? You're getting more and more friends with time. Did you guys hear that? Okay, so this is what's also called in business first mover advantage. So the notion that within this model, you don't have a chance if you come late into the game. So anybody who arrived later than the green guy will always have less friends than that guy at the same moment of time. See that? It doesn't matter. We can compare it here. We can look at here. We can look at here. Yes, each of them grow number of friends, but you can never beat the guy who was earlier than you in this game. Right? Now, again, well, luckily life is more complicated. This is just a property of the model. But this model, it just forces it, right? And so pretty much if your life is organized that way that, the only 2 things counts, which is you come and you make those connections, you will never become more popular person. It's always the people who were before you will be more popular. Okay? Or you invent your own social network, right? Okay, so you cannot beat old money in some sense. All right, so this is an example of power law graph build. This is an example of graph built using this preferential attachment model. And within every node, I actually put a node number, and node number they just numbered by the arrival, right? So node number 2 arrived before node number 7 to be right before node number 9. Node number 20 arrived before node number 39, etc. In this model, it is very simplistic. Every node, when it arrives, just makes one connection. The point I'm trying to make here is, of course, that the nodes that arrived earlier will be more central, and on average, will have higher degrees than the later arrivals. And if you notice, yes, node 1 is well connected, node 2 is well connected, node 9 is well connected, node 20 is well connected, and the later arrivals, they have much fewer connections. Okay. All right. Now, this model, on one hand, like, okay, fine, you came up with those restrictions, those rules, you build a model, so what? Interestingly enough, that this model actually exhibits this power law distribution. So within this model, you will have a few nodes with very high degrees, and the majority of nodes will have low degrees. And if I actually draw this as a distribution function, which is a node degree, and this is a this is a probability of having that node degree, it actually goes that way. It drops very fast. And if we take it logarithmically, it's going to be a straight line, as we discussed in the previous lecture. And so, that property made the model famous because it just says, oh, okay, you have this very strange and unusual power law distribution of the nodes. Well, the reason for that is because we have this hypothesis that happens because of preferential attachment, right? So this dynamic plus preferential attachment creates the power law distribution. And we observed in real life power law distribution. So we believe that life is working that way. It's exactly what we discussed at the beginning of the lecture, that you make certain hypotheses, and then you verify them with a model, right? Based on that hypothesis, we build a model. We look at the properties of the model, and we see that it has this power law distribution. Well, maybe that sort of, it doesn't completely prove that our hypothesis is correct, but it tells us, like, yeah, maybe that's the way life is. This is comparison. Where do you think we have a preferential attachment, and where do we have a random graph? These are two different graphs, the same number of nodes, the same number of edges on average, approximately the same should be. Which one is random graph? Which one is preferential attachment graph? And the size of the node is proportional to the node degree. All right, guys, back there. Do you agree or disagree? Okay, who thinks that the random graph is on the left? Raise your hand. Who thinks it's on the right? Okay. Who doesn't think? All right, look, you're right, and why is it this random and this is its preferential attachment? Yep. And so first of all, here we have those kind of, connected things, right? But the biggest difference is the distribution of node degrees, right? Here you have, nodes of decent size and a lot of them of similar sizes. Right here, there are some nodes which have much higher size, right? Much more connections. Very uneven degree distribution. That's power law degree distribution. This is Poisson. I know that's maybe subtle, but when you see those graphs, you can actually see the difference. It's noticeable. Just a few examples. When I build this preferential attachment model, again, lucky you within R and the package iGraph, there is this barabashi.game function that just generates those models for you. You can give as a parameter number of connections, Every time when the node comes in, if it gives you one edge or two edges or three edges, that's what the graphs looks like when you generate them. Going back to like major properties, as I said before, the degree distribution is a power law here. And it is probability of the node that has degree k is inversely proportional to k cubed. So what that means, if you know the probability that the node has degree 2, right, is going to be whatever the constant here divided by 2 to the third power, which is 8, right? 1/8. Probability that the node has degree 10 is going to be whatever constant is divided by 10 cubed, which is, what's 10 cubed? 10 times 10 times 10. What is it? 1,000, right? So if you have node with, so what happens is the probability of the node of having a node with degree 2, which means, having two neighbors, 1/8. Of degree 10, 1/1000. So feel the difference? There is a huge difference in those probabilities. So the degrees are not that different, 2 or 10, but 2 is much more likely than 10 in this type of graph. All right? Okay, now, average path length here is also, you can also see this small world phenomenon, which is logarithmic of number of nodes. And there is some clustering coefficient. You cannot compute it precisely. I know you don't care, but the point is there are some triangles, not that many triangles. So this model, if we think about how well it describes the real world, the networks that we see out there, yeah, it actually describes pretty well the node degree distribution, the fact that we do have those celebrities that have lots of connections, like most of the connections are to them. There are a few of those. And the majority of the nodes have low degree connections, and that kind of reproduces it. It also shows out that there is a small world phenomenon, right? So you can reach pretty quickly nodes from one node to another, so it's logarithmic in the number of nodes. It doesn't give you any triangles in the graph. So again, it's a model, has good things and bad things, right? Bad things in the sense, it does not reproduce the reality exactly. But it has very nice sort of explainability of this power law. Any questions about this model? All right. So as I mentioned at the beginning of the lecture, this is really sort of a starting point, right? So now when you understand how those models are being created, so you take the randomness, you add certain properties, right? You add certain restrictions, you add certain dynamics, certain ways to actually construct graphs. You can build your own models and implement them and see how they evolve with time, right? Okay. One last model, which is called small world model. Here is a story. Take a look at this strange graph, right? Now, it's actually very strange. The reason for it to be so strange is because it's also, these guys are going to talk about, they're physicists, and, in physics, you often, when you try to solve some, physical/mathematical problems, you try to avoid what's called boundary conditions. You try to avoid the situation where you need to describe what happens at the end, at the edge, right? Because that kind of disturbs your thinking. You need to spend a lot of time to describe that, and that's why you try to make shapes that don't have boundaries as much as possible, right? Like one of the favorite shapes for theoretical physicists will be a donut. Why? Because there's no edges, right? Think about donut. It's beautiful, right? So there's no edges. You can walk as much as you want on the donut, right? And there's no edge. So, okay, so these are physicists. So, okay, we're lucky they didn't form a donut from this, though they could, of course. But for the simplicity of the reader and convenience of the publisher, they actually just made it a circle. All right. Now, what's interesting about this graph? Notice there are like lots of triangles, right? So in some sense, if you actually calculate clustering coefficient, is equal 1/2. Why is it 1/2? Well, because you take this guy, he has this neighbor, this neighbor, this neighbor, this neighbor, right? 1, 2, 3, 4 neighbors, and here's the connections. The only connections that I'm missing is from this node to this node, this node to this node, this to this. So half of the possible connections are present in here. And so it's very, very triangulated graph, right? Again, in social network, you hardly find that many triangles. But again, this is a modeling exercise. So, let's say we have this graph that has lots of triangles, very strong clustering coefficient. Now, what's the problem with this graph? What's missing? Well, notice that there's not that many nodes in here, right? How many nodes are here? Like 1, 2, 3, 4, 5, 6. Okay, probably like also, probably around like 30 nodes. What's the diameter? How long would it take you to get from here to there? Well, yeah, it says 8. Do you trust it? You need to check, right? Okay, 1, 2, 3, 4, 5, 6. Well, yeah, 8. All right, I'll go this way. 1, 2, 3, 4, 5, 6, 7. All right, fine, 8. So it's large, right? Remember, 6 handshakes that separates the world. So if we arrange 7 billion people in a smart way, you can actually reach, in 6 steps, each and every person. And here, like 30, and you still need 8 steps. It is ridiculous, right? So now imagine that you have the power to actually, change this graph, but you want to keep the triangles in place, or most of the triangles in place, right? So you want it to be triangulated. You want to have like friends of the friends knows each other, right? You want to keep this property. What would you do? But you want to have it a small diameter. You want to make it a small world. Yeah, you can, for example, make it like twist and make it 8. You're thinking like physicists. You're like, shapes. Exactly. You can, for example, take a node here, and like shortcut them, right? Make a connection here. Like add just a few edges, not that many edges, but connect this to this, connect maybe this to this, maybe this guy to here, and all of a sudden, on one hand, you will keep triangles. On the other hand, you will create so many shortcuts, it'll be very, very easy to get from one point to another, very quickly. Right? By the way, for example, Moscow, for a long time until like recent renovation, was like that for drivers. Think about this as a garden ring. There were tons of ways to get across it, right? Along the Moscow River, there was like a lot of streets. Now, because they're all one way or blocked, you have to go around here, and we have traffic jams from morning till night. So that's a great example of people doing something they shouldn't be doing. Anyway, we know how to fix it, make shortcuts. That's what guys proposed in 1998. Now, if you do not want to change the number of edges, I mean, this is like slightly different picture, but that's the same story, right? It's the same kind of triangles here. If you don't, and this is a figure from original paper. If you do not want to add new edges, what you can do, you can sort of disconnect maybe here and use this edge to connect further away, right? Or disconnect here and connect further away, and do it randomly. So if you take and rewire the whole thing, you'll get a random graph, because all of a sudden everything will be connected randomly. But if you rewire part of the edges, you will keep actually two nice properties. You'll keep this triangulation, which means very easy local movement, right? If you think about transportation, or in other words, it's also friendship, but you can also have long connections. By the way, in the real life, there is something that organized this way. What's that? In transportation. Think about airlines and airports. How do they work? Today, it's what's called hub and spoke model, right? There are big hubs, like long-range connections. There are flights from, there are a big hub in Paris. There are a big hub in, say, New York, Chicago, LA. Those are long-range connections. And then there are a lot of local connections, right? If you ever seen airline maps, how they fly from big hub to big hub. And then there's lots of local services. And that on one hand, and that actually optimizes the travel time, right? It minimizes the number of hops you need to go from one place to another, right? In some sense, it's sometimes it's maybe not very, sometimes it's less efficient than you want it to be, but the idea is, again, you have Moscow as a big hub, you have Paris as a big hub. If you want to travel somewhere in France, what you do? Well, you get to the Moscow airport, right? Then there is a long-range flight to Paris, then you go from Paris to local flight in France, right? So, and that's pretty much the same story. Local, long-range, local, right? If you want to get somewhere in a few steps. Okay, all right. So that's the model, and here's an example. In fact, again, Watt-Strogat's game, there is a function, and you can play with it. And the idea is the following. You can give some graph, and I just gave, this another strange-looking graph, but it has, a bunch of triangles also in it. And so average path length here is 358 on this particular graph, and clustering coefficient 0.49. Well, it should be 0.5. It's 0.49 because of the edges. So clustering coefficient is very high, but average path length, is pretty big. I did 20% rewiring. So I took 20% of the edges that connects it and randomly connected it somewhere else in the graph. And by doing so, on one hand, I was able to reduce average path length. On the other hand, yes, I dropped clustering coefficient, but not very much. So there is still triangulation, there is still sort of local properties, but there is also a way to get across at the large distances. And so the Watt-Strogat's model is really about this. It's about finding the balance in between the triangles, right, in between local properties and long-range properties, long-range distance. And what they try to show in their model that those two things can coexist. On one hand, you can have triangles in the graph. On the other hand, the graph can have small diameter, right? Small average distance. Well, they did it quite artificially, right, by actually just doing this rewiring. But the point was to show that it works and also give you an instrument. Remember, this is generative models, which means it tells you how to generate graphs with certain properties. And that tells you, like, okay, you have a graph with a lot of triangles. This is good, but your length is your diameter is too much. What you do? Well, you change it and use this random connections to do it. It's a model, again, not perfect. Again, you can modify it the way you want. You're saying, like, okay, I don't want to connect to the nearest neighbors. Well, fine, you can put the constraint saying you have to connect, 3 steps away, right? Or you don't want it to do it in a certain way, you do it in any other way, all right? Within this model, no degree distribution is not really good because, it's kind of Poisson-like, but the average path lengths can be very small because, you do these connections. And the clustering coefficient is those triangles, which is good. So it's actually reproducing, keeping this, two friends know each other thing. So what we've done today, these are empirical networks, right? Those that we kind of know from nature, those that we measured in experiments, Facebook graph, friendship networks. Most of them exhibit this power law phenomenon, right? With one more time, there are like some nodes with a very, very large node degree, majority of the nodes with a low node degree, so very much skewed distribution, this power law distribution. Empirically, clustering coefficient is quite large, especially in social networks. So again, two people, two friends know you. Sorry. Two of your friends usually know each other. And there's 6 handshakes that separates the world. So again, there's very small average path lengths in empirical networks. What do we see in our models? Well, in random graph, the distribution is not power law, it's Poisson. Clustering coefficient is bad, but it's a small world network. But it's a pretty cool network, and there's a phase transition here. Barbashi-Albert model has power law degree distribution, has small world, a little bit bad on clustering. Watts-Strogatz model, Poisson-like distribution, which is not good. It's actually constant, a very strong clustering coefficient, which is good, which is large, and it is also small world. So looking at those 3 models, neither of those models actually match the empirical networks, but they give us an idea of how parts of those networks can be organized, and they also give you a lot of thought and a lot of food for thought in terms of like, okay, each of those models gives you some properties that are good properties to describe networks. You might actually take and combine those models in some way, and that creates lots of dissertations, master degree thesis, et cetera, like working for those models. Any questions here? Okay, this is a list of references. One last question before we're done today. So, why did we actually study these models? What was the point of this lecture? Okay, but why did we do that? I mean, why do we want to know this? In some research, right. So it's pretty much the same question with which we started today. We do this because we would like to, the models is something we can experiment with. We can have some hypothesis about the way the real world is created. And this is a playground that allows you to check on those hypotheses, verify them, and build the networks. Okay? All right. Thank you. Done for today.